For our final lesson dealing with surface area and volume, we're going to focus on the surface area and the volumes for spheres. And we have already developed an understanding of these four formulas. I say four even though there's six listed there because these two formulas are essentially the same and these two formulas are essentially the same. The only difference again is pyramids have perimeters around their base and cones have a circumference around their base. Prisms have a perimeter around their base, whereas cylinders have a circumference. So it's just a language difference and just making sure that we're using the appropriate letters. Otherwise, there's just four formulas here for prisms and cylinders, pyramids and cones. And then we're going to add two more today dealing with spheres. So we're going to find the surface area of a sphere, we're going to find the volume of a sphere, and in order to do that, we need to know a little bit about those things. So here's some key vocabulary dealing with spheres. Obviously, a sphere is kind of the set of all points in space, 3D space, that are equidistant from a point. It's basically the three-dimensional version of a circle. And in a plane on a flat surface, all the points that are equidistant from that center point make up the circle. Well, in three-dimensional space, all of the points in space that are equidistant from that center create a sphere. That center is obviously that main place. That distance is referred to as that radius. And the diameter is the distance all the way across the sphere. All right? And so we're going to have a lot of similarities between how we work with circles, how we work with cylinders, how we work with cones, and then of course how we will work with spheres. We're going to have some basic formulas. We're going to be using pi. We're going to have radii and diameters involved in this conversation. A great circle is kind of like the equator, right? It's a circle that goes all the way around the sphere. But any of those longitudinal lines that wrap all the way around the Earth, those would also be great circles. Our latitudinal lines would not be considered great circles because those latitudinal lines or circles are actually shorter towards the poles, but then they're a longer distance around the center. And so if we were to take that equator and tilt it around the Earth, that distance would give us a great circle. All right. So a great circle is basically a plane that cuts through a diameter of the sphere. The circumference of that great circle is the circumference of your sphere, and hemispheres are basically a fancy name for saying a half of a sphere. So you're probably familiar with a lot of this terminology. We're going to have the same formula for circumference. The great circle, again, you're going to see those drawn. You don't necessarily need to recite that vocabulary, but as we talk about those things, want to make sure that we understand what we're saying. And so here are the two new formulas for surface area of a sphere and the volume of a sphere. You're going to notice that this is going to look pretty similar to the area of a circle. We just multiply that area of that great circle by 4. And then over here, we have another exploration dealing with volume. All right, we have 4/3 times pi times the radius to the third power, the radius cubed. Now remember, squared doesn't mean times 2, it means times itself. Likewise, cubed doesn't mean times 3, it means times itself and then times itself again. So 2 to the third power is 8 because 2 times 2 makes 4 and 4 times 2 makes 8. 3 to the third power is 27. 4 to the third power is 64, etc. Let your calculator do that multiplication if like you did with squares. Even though you know your squares from your elementary times tables, we still use our calculators to multiply that a little bit faster. And then again, to multiply that by 4, we're going to have the same thing here. So let your calculator do that work of multiplying 4/3 times the radius cubed, and then take that and answer in terms of pi. Tack that pi onto the end. So here are a few examples. These will kind of go in quick succession, so if you need to pause the video at any time to draw the picture, write the formula, do the work. If you want to get ahead of me and try to do this before I post the work, that is an awesome idea. And so what we'll see here is that here we have a sphere with a diameter of 18 feet, and the surface area formula is 4 times pi r squared, and so we'll have 4 times pi times 9 squared, or 4 times pi times 81, which gives us 324 pi square feet. Finding the volume, we've got 4/3 times pi times the radius to the third power. And just like there's an order of operations here, I don't do 4 times 9 and then squared, I do 9 squared and then multiply by 4, following PEMDAS. We're going to do the same thing here. We're not going to take 4/3 times 9 and then cube it. We're going to take 9 cubed and then multiply by 4/3 and say we have that many pi. In this case, 972 pi cubic feet. You'll notice that these numbers are large. And the reason is because we're dealing with an exponential situation. It's not that we just have 4 and 9. We've got 4 and 9 and then another multiple of 9. Here we have 4/3, a fraction bigger than 1, and then we're multiplying that by 9, and then we're multiplying by 9, and then we're multiplying by 9 again. So we have 9 times 9 times 9, so 81 times 9 gets pretty big, and then we have a number that's going to be bigger than 9 to the third power, all right? So we get 972 pi, and our units for volume are cubic units. Our area was square units, our volume is cube units. If we're cubing, we get cubic units. If we're squaring, we get square units. Over here, the diameter is 30 centimeters. So that means that our radius is 15. 4 times pi times 15 squared, or 4 times 225, gives us 900. 900 times pi is 900 pi square centimeters for area. On the volume side of things, 4/3 times pi times 15 is going to give us 4/3 times 15 to the third power. This is going to give us a pretty large number here, 4,500 pi, or 4,500 pi. You'll notice that even though we have a fraction here, I'm not ending with a fraction in my answer. The reason is because this radius is divisible by 3. So when we cube this number, we've got a factor of 3 in there, 5 times 3 and 5 times 3 and 5 times 3, but one of those 3's is going to cancel with this denominator here. They're going to make a factor of 1, and so that's why we have a situation where we have a fraction in our work but not a fraction in our answer. If this number were a number that is not divisible by 3, then our answer is going to be a number that has 3 in a denominator. All right, as we're going to see in this situation. Here our diameter is 14, which means our radius is 7. And so on the surface area side, things work out fine. 4 times 49, we get 196 times pi, and that's squared units, whatever our units are. In this case, it's inches. But on the volume side of things, don't let this confuse you. Let the calculator do the work. Just like you're letting the calculator do the work here. I know that at times when the math works nice and easy, where it works out where we have a whole number answer, we're like, word. Over here, however, we've got a situation where we're taking 4/3 times 7 times 7 times 7, all right? And so we end up with a very large numerator, all right? A very large numerator over 3, all right? Because 7 doesn't divide by 3, and neither does 4. And so if you have 4 times 7 times 7 times 7, that number does not divide by 3. So we have that number over 3 times pi. Again, a reminder, just like we talked about in the last 2 lessons, if you want to have the pi in the numerator there, that is completely okay with me. How about if our sphere has a radius? Again, sometimes they give us the radius, sometimes they give us the diameter, the radius of 30 meters. Go ahead and give this one your best shot without using me. You do this one on your own. All right. For our next example, dang it. We're going to deal with what if we are given some other information and we need to work that backwards to find out what the radius is so we can use that to find our surface area, or if there's some other shortcut. So if we know what the circumference is, and we can measure that, we can take a ball and we can drag a string around the outside of that ball and we can find out what the circumference is. And if we find out that that circumference is 13 centimeters, we can kind of get by just knowing the circumference without necessarily knowing the radius. All right, and so this is kind of an awkward approach, but we measure this in a solid amount of inches there. We're not measuring that in terms of pi because our calculators don't, or I'm sorry, our measuring tape doesn't work that way. And so this means that we're probably going to have to end up approximating our surface area. And so in this case, we have the circumference equals 2 times pi times the radius. Or we can kind of consider this notion that the circumference divided by pi, divide both sides by pi, is going to equal the diameter, all right, 2 radii. And so we can use that to understand, using a little bit of algebra 1 factoring here, separate out this 4 pi r squared as 2 times pi times r, and we'll notice that we have a 2r and a 2 pi r. Well, 2 pi r is our circumference, and 2r is our circumference over pi. Just kind of a strange exploration, doing some fancy algebraic manipulation here. And this gives us 2r times the circumference, or the circumference over pi times the circumference. So not even knowing what the radius is, we can take the circumference squared and divide it by pi, and that will tell us what our surface area is. It's kind of a neat trick. We can take 169 and divide it by pi, and in this particular case, we could approximate that value to be 54 square centimeters. This is the one time so far in all of our notes and examples where we've gotten to approximate a value for our surface areas. Likewise, we might have a situation where we are given the volume and we need to work that in reverse to find the surface area. This will be challenging in that we have to be able to undo cubing using our calculator. So just like there is a square root operation that we get to use in our calculators or using our elementary arithmetic, there's also a cube root operation where we can undo cubing using a cube root. And you wouldn't have explored that in Algebra 1. You will explore that in Algebra 2. We will lead you into that by doing this practice here with our calculators in geometry. So the idea of taking a square root is we use this radical button. So if I'm taking the square root of 169, I will get 13. And I'm not sure how well you can see that, but the square root of 169 is equal to 13. But if I wanted to take the cube root of a button, then I have to do some special operations. I have to press the number 3, and then not the square root, but the x root button, the cube root of, let's say, 64. I already said earlier that the cube root of 64 is 4, and we can find out here that when I do that cube root of 64, press enter, it'll give me that output of 4. So I press 3, second, and then right above the square button, oops, that's a little blurry, is the exponent button, and that will let us do the x root. So we're taking the third root of, and then we can pick another number like 27, and the cube root of 27 is going to tell us that the answer is 3, so we can find that cube root. Having a scientific calculator is helpful. Your calculator may be a little bit different than that old thing, but you guys get the idea. If we know what the volume is, we can work that in reverse to solve for the radius doing Algebra 1. Divide by 4/3 or multiply by 3/4 on both sides. Divide by pi on both sides. And then we're left with something equals the radius cubed. We then have to take the cube root. So watch what happens. 288 pi equals 4/3 pi r cubed. Divide both sides by 4/3 or multiply both sides by 3/4. We're getting a number that is smaller than 288 pi. We can then divide by the pi's on both sides, and we're left with 216 as the radius cubed. Using our calculator to take the cube root of 216, we'll find out that the radius is 6. All right, and the units here are feet. So we have the radius. Now we can use that in our surface area formula to take 4 times pi times 6 squared, which we may have even done earlier in this work here. 4 times 36 gives us 144 pi square feet. We started with cubic feet in terms of pi. We ended with square feet in terms of pi. All right? At times, you may be given a volume that is in just feet. It's not in terms of pi, and we're going to get an answer that's going to be approximated, all right? Because things are going to get a little bit messy when we divide by pi and then we multiply by pi again. So it's going to get a little bit awkward there, but we're going to do our best work. All right, that is it. That is the end. Surface area of a sphere, volume of a sphere. Make sure you know those formulas of 4/3 pi r cubed for volume, 4 pi r squared for surface area. Let me know if you have any questions from this video, and I'll see you in class.